Good morning and good afternoon to all our participants, and welcome to today's webinar, which is on the surface area determination and surface energy calculations using inverse gas chromatography. I'm Dr. Sabiyah Ahmad, an application scientist here at Surface Measurement Systems, and this webinar will present the theory and calculation process of the BET specific surface area and surface energy analysis using inverse gas chromatography and comparison with other techniques. Inverse gas chromatography can be used to measure both finite and infinite dilution experiments depending on the requirement and the application. The BET specific surface area analysis is a finite dilution experiment which requires saturation to monolayer coverage of the surface with the vapor phase probe molecules and where solute-solute interactions occur. Today's presenter is Dr. Anett Kondor, who is the iGC-SEA product manager and product specialist at Surface Measurement Systems. Since 2004, Anett has been working on gas chromatographic GC and IGC techniques. She studied chemical engineering at the University of Pannonia in Hungary, where she received her MSc in chemical engineering, accredited by the British Institution of Chemical Engineers, and her PhD in chemistry and environmental science. She's published several research work in peer-reviewed journals and collaborated with research groups around the world. So before we begin, just like to request all our participants that during the presentation, you just mute your microphones. And after the presentation, we'll have to take any questions, so you can either use your mic or the chat box at this time. And now I'm going to hand over to Anett.
Thank you, Sabiyah. I hope everyone can hear me. Welcome for everyone. Good morning, good afternoon, and good evening. I saw there's some attendees from Japan. Probably it's a bit late over there. Today's webinar is about determination of specific surface area and surface energy using inverse gas chromatography. So first, I will just introduce the technique, and I will talk about then the BET surface area analysis using IGC with an example on natural fibers. And then I will go through the determination of surface energy using IGC technique. And I hope we'll have time to show you an example on this as well, on a fiber. IGC technique was developed in the 60s. It's mainly used to measure surface energetics of solid materials. Nevertheless, it's suitable to determine other physical-chemical properties of solid materials, such as adsorption isotherm, heat absorption, solubility parameter, and so on. IGC is especially suited to fibrous and powdery substrates, but it can be also used to other type of morphology samples like granules or some other materials like films or membranes. We also used to measure some sponge with IGC. IGC was developed in the 60s, and at the beginning, everyone just used an analytical GC by converting it to IGC measurement. SMS is the first company, and so far the only one who's producing commercial IGC system. And we call our IGC instrument SEA, Surface Energy Analyzer. IGC, the principle of IGC is actually the reverse of the analytical GC. In case of analytical GC, the solid phase is known, and what we inject, the mixture and the compounds, is what we investigate actually. And during this analysis, we can get quality and quantity information about the injected compounds. So this technique is a kind of separation technique. And IGC is a characterization technique. It's used to characterize the solid phase which is in the column. So in this case, what we investigate is the solid phase. And what we inject through this column is a known pure organic solvent. And we inject the single organic vapors through the column, which is packed with our sample. And we measure the retention time of the different organic vapors. And from this retention time, the different physical-chemical properties can be determined. Because this retention time will indicate the interaction strength between the solid surface and the injected probe. On this slide, you can see the schematic of the IGC system, of our IGC system. The carrier gas is helium or nitrogen. The oven has 2 column positions, and it has a special design. It's really designed for thermodynamic measurements. And the standard oven has a 20 to 150 degrees C operating range. And our instrument is an automated injection system based on the gas phase injection, like a head space injection. And we have a very unique and user-friendly control and analysis software for the instrument. So everything is automated, and it's very easy to operate and also to analyze the data. The instrument has features like humidity option or film cell device to measure films or plate surface properties as well. The humidity option, I think, is one of the most unique and one of the most important benefits of our instrument, because the impact of the relative humidity on the surface properties can be measured with this option. And it's very important to know how the humidity, how the humid environment can affect the surface energy or the surface area. Because there's humidity everywhere during production, during storage, or during the application of the solids. And how this humidity could affect the surface properties is important to know. IGC has, our iGC-SEA system has a glass columns with different inner diameters, as you can see on the picture. And these are straight sterilized glass tubes, all of them 30 centimeter long. These are non-reusable columns. And once you pack the column with the sample, you can use for the different type of analysis, because the measurement is non-destructive analysis. On our YouTube channel, you can watch some videos about column packing and sample preparation. If you are interested in how to pack a column with a fiber or with the powder sample. With IGC technique, you can determine different physical-chemical properties of the solid materials, and not just BET specific surface area and surface energy. But you can also measure the acid-base interactions on the surface, the solubility parameters, or the diffusion coefficients of different gases, and so on. We constantly implement new applications or new features to our analysis software. So currently, we are working on a chemisorption application, and hopefully we'll have some nice application notes on that. So first, the BET specific surface area analysis of solids by gas adsorption. To apply the BET method, you have to measure gas adsorption isotherm. The gas, the adsorptive, can be any gas which physically adsorb on the solid surface, which means a weak bond, van der Waals forces. And also it means that at the same temperature, it can be desorbed from the surface. Nitrogen adsorption measurement carried out at 77 Kelvin. It's the boiling point of nitrogen. And nitrogen is the most suitable adsorptive, but it's not standard for every industry. It's just the most commonly used adsorptive. There's other adsorptives which is in the ISO standard, listed in this ISO standard, what I referred. And you can see that organic vapors can also use to measure gas adsorption for BET method, like heptane, octane, or benzene, and also water. The benefit of these probes that you can measure the adsorption isotherm at room temperature, ambient condition. You don't need a liquid nitrogen condition, 77 Kelvin, which is quite an extreme condition, especially for organic samples. For inorganic materials, which are more rigid and they are not sensitive for different conditions, probably nitrogen condition is suitable, but for organic materials, ambient condition, it's more recommended. Because at very, very low temperature, some structural changes can happen in the sample. To apply the BET method, there's two types of isotherm, the type 2 and the 4, based on the UPAC classification, which is suitable for the BET method. And during the BET specific surface area measurement, only the surface, which is accessible for the probes, is measured. And during the analysis, at least 4 points within the relative pressure range for BET equation is required. So the BET relative pressure range is from 0.05 to 0.3 or 35. And within this relative pressure range, you need minimum 4 points to get to fit the BET equation and to get the specific surface area. There's different techniques what you can use to measure adsorption isotherm, like the volumetric technique, volumetric nitrogen adsorption technique, and the dynamic vapor adsorption technique also can be used to measure adsorption isotherm. It's based on a gravimetric method. And also carrier gas method is a technique what you can use to measure adsorption isotherms, like IGC. The benefits using IGC that the degassing is in situ, and you can measure the adsorption isotherm at ambient condition, and you can use organic vapors. The BET surface area can be in a very wide range, and normally nitrogen adsorption technique is used to measure the BET specific surface area. It's very accurate, especially at the high surface area. As you see, the relative standard deviation is about 1 or less than 1. around 1,000 meters square per gram surface area. IGC can't measure that high surface area due to the pulse injection, but it's really accurate and applicable in a low surface area range. Whereas other techniques struggle a little bit, and the accuracy is not that good. DBS also can be used in a quite wide range of surface area, and because during the measurements, the organic vapor concentration is constant in the carrier flow, so it's a little bit different type of measurements compared with IGC. In the table, you can see the measurement parameters and which kind of adsorptive gas you can use, and also the pressures. So to measure adsorption isotherm with IGC technique, you have to inject a solvent at different concentration, and once you injected the selected adsorptive, for example, the octane at different concentration, you can determine the partial pressure and the retention volume from the different from the series of injection, and then from that plot easily with the integration, the adsorption isotherm can be determined. And this adsorption isotherm can be used to determine the BET specific surface area, or the adsorption capacity, or a Henry adsorption constant as well. We perform the validation of our IGC instrument using standard reference materials like this alpha alumina sample 170, which is a reported BET surface area value 1.05 meters square per gram. During the measurements, we used a 500 milligram sample. The octane isotherm was determined at 30 Celsius. Before the adsorption isotherm measurements, in situ conditioning was applied at 100 degrees C for 6 hours. The surface area, what we determined using this octane isotherm was 1.01, which was really close to the reported value. And the validation of the instrument contained other reference materials as well, what you can find in the application 225 if you are interested in the validation of the technique. We also performed a reproducibility study for BET specific surface area, so the reliability of the instrument on surface area. During this study, we used paracetamol, commercially available paracetamol from Sigma Aldrich, and we packed 22 columns. Each column contained 250 milligram samples, and on the first 10 column, we repeated the experiment 10 times and determined the experiment-to-experiment reproducibility. As you can see on this slide, and it was less than 1 or maximum 2, the reproducibility. The surface area of the paracetamol is very low, is less than 0.3 meters square per gram, as you can see. And with IGC technique, we could determine very accurately this surface area, whereas other techniques struggle to measure accurately the surface area. So IGC, as you can see, is very applicable at low surface area. And now I'd like to share with you some advices, some practical advices, how you can set up a method in our software, so in our control software. When you create a method, there's two different injection options if you have the advanced software. So you can inject in surface coverage or in moles. I usually select the surface coverage injection. It's much easier to work with. And if you select also the surface coverage, then when you create the sample ID, the BET, the initial BET is to be overestimated. So like in case of this sample, just created an example. So if it's a lactose monohydrate, usually lactose has around 1 meter square per gram surface area. And in case of this low surface area samples, around 500 milligram sample or less than 500 milligram sample is enough. And as you see, the BET, the initial BET, what I entered is because I definitely want to reach the monolayer coverage, so I want to oversaturate the surface with the probe. So that's just a practical advice. So if you use the surface coverage injection, that's what you have to do to trick the system. But of course, if you use the moles injection, you don't need to do this. And then once you created the sample ID and selected the type of injection, you can create the method. A series of, as I mentioned, a series of injection from a probe, in this case octane, or you can use also heptane, is to be inserted. And I usually start with the highest achievable coverage injection, and then I reduce the concentration, as you see. So going down to the smallest concentration. And there's only just a practical reason why I choose the highest achievable surface coverage. Because the BET specific surface area can be determined in a specific relative pressure range. So the BET relative pressure range is from 0.05 to 0.35. So once the first injection performed in iGC-SEA, we can analyze it while the experiment is running. So if the first injection is in the highest relative pressure range of the BET relative pressure range, I leave the experiment to complete, to finish, because the rest of the injections will be under that point. So I will have enough data points in the BET pressure range to analyze the BET specific surface area. But for example, if the first injected if the first injection is in a lower relative pressure range, so for example, around 0.1 or less than 0.05, that means that probably I will not have enough data points in the BET pressure range to analyze accurately the BET specific surface area. In this case, I just stopped the experiment and changed the sample ID, because probably I underestimated the BET specific surface area of my sample. So using a higher BET surface area, then rerun the method, probably will get higher relative pressure points. We have a BET troubleshooting guide, and it's available also in Chinese as well. So if you can contact with us, or probably have this guide help you to perform the BET experiment most accurately, and it's available also on our website. So I recommend you, if you just start BET analysis with IGC, this also contains a nice summary of the BET analysis. So just quickly, like to show you a case study on the BET surface area analysis of some natural fibers. During this study, we analyzed 3 different fibers. One was a cellulose fiber, which you can see on the first picture from the left side. It's a biamide fiber, and you can see the surface of this cellulose fiber is quite uniform. There's no defects on the surface. Also, we measured another 2 glass fibers, a KNF and a flex fiber. The surface of these 2 natural fibers wasn't that smooth, and you can see there's some defects, and especially in case of the flex fiber, there's a lot of irregularities, surface irregularities. So we packed the fibers into our formulae columns, and we performed the experiment 3 times in order to determine the relative standard deviation of the experiment. And you can see in case of those fibers which had a uniform smooth surface, the relative standard deviation is not that high. It's excellent, smaller than 1%. In case of the flex fiber, which was the most irregular, we measured 3.5 relative standard deviation. The surface roughness, as you can see, can affect the reproducibility of the results, but it still has an excellent reproducibility using IGC. Then we also performed the batch-to-batch variability measurement. So we packed several columns, and we determined the surface area of the different fibers. In case of the cellulose fiber, commercial cellulose fiber, you can see that the reproducibility is quite good. But in case of the natural fibers, the deviation is much bigger, and also again, the flex fiber showed the biggest deviation. Natural fibers contains some irregularities on the surface, and they have heterogeneous properties. And it depends of a lot of different things, harvesting, the growing condition, and so on. So that's basically what we expected, but still the reproducibility was quite good, the batch. If you are interested more in this case study, I recommend you the publication, what we wrote about this. And during this study, we also investigated the adsorptive effect on the surface area, also the flow rate effect, and the sample preparation effect. So we also chopped the fiber once, and repacked the column with the chopped fibers. But normally we used a very long fiber. So I strongly recommend this publication if you interested in the BT surface area study. As I mentioned, yeah, the humidity option is quite a huge advantage of our instrument, because we can determine the impact of the relative humidity on the surface properties, like on the surface area. You can see that the reference material, this alpha alumina sample, surface area with the dry carrier gas, if there's no humidity, it's 2.95, which is the reported surface area value of this sample. If we apply 50% relative humidity in the carrier, you can see that the surface area now is a little bit smaller. Using 90% relative humidity, the surface area is half of the original, the dry conditioned surface area. You can see that how this relative humidity affects the available surface. Because if there's humidity, water vapors will absorb on the surface by the can and will block the available site by reducing the surface area, the available surface area. Here's an example, for example, in case of cotton, how the humidity affects the surface area. And then in this case, you can see that the surface area is increasing because water absorbs into the cotton, the filaments, and increase the distance between the filaments. So there's the effect of the humidity is always depends of the sample. It's not always there's not always a decreasing trend or an increasing trend. It depends really of the sample, how it will behave under humid condition. So the next part of my presentation is determination of surface energy using IGC technique. Surface energy is the most common measured property by in-base gas chromatography, and it's analogous to the surface tension of liquids. The definition also says that surface energy indicates the maximum surface tension of a liquid which wet the solid under ideal condition. And the surface energy is also used to quantify the ability of the surface to react compared with the bulk. In the bulk, atoms surrounded with other atoms, and they interact with each other. But on the surface, atoms only interact towards to the center. So some surface electrons can react with the surroundings atoms or molecules, and the willingness of these electrons to react with the surroundings shows the ability of the surface to react. Surface energy can use to determine also the work of adhesion, the thermodynamic work of adhesion. And surface energy has different components. Folks was the first who expressed the surface energy with different components, dispersive and different specific parts. So the surface energy symbol is the gamma, like the surface tension, but there's an S which indicates that it's related to solid. So the total surface energy has different components, dispersive and specific, or it's also called Lewis acid-base component. And this contains the chemical short-range interactions. The dispersive part contains the London van der Waals forces. And the unit is the same with the surface tension, it's joule per meter square or millijoule per meter square. Surface energy and its components between two interacting surfaces are critically important in a number of industrial applications, including adhesion, coating operations, printing, lubrications, and so important in daily life biology as well. The knowledge of the surface energetics is important in formulation design of multi-component systems and the prediction of processing performance. In the case of IGC analysis, we use an extended approach, the Folk's theory. So where's the specific part of the surface energy divided for acid and the base parameter. So during the analysis, we determine the dispersive part, an acid and a base component of surface energy. And from the acid and the base components, we determine the specific part. So how we determine from the retention parameters the surface energy. So what we measure is the retention time of the probes. And also we use an inert gas, well, methane, to determine the time of the system. So from the retention time and some other measurement parameters like flow rate, temperature, and sample mass, and the column pressure drop, we determine the specific retention volume. And this specific retention volume is used to determine the Gibbs free energy. And this Gibbs free energy is the y-axis on the plot of surface energy calculation. There's two different methods to determine the dispersive surface energy component, both based on a series of injections of alkane, normal alkanes. And in case of both methods, the Gibbs free energy of the alkanes used, it's on the y-axis, and the x-axis, depending on the method, it's the carbon number or the cross-sectional area and the liquid surface tension of the probes. I recommend to use the Dorison gray, especially at elevated temperature, higher than room temperature, because in this case, the surface tension of a methylene group is corrected with the measuring temperature. While in case of Schultz method, the cross-sectional area and the liquid surface tension of the injected probes are measured at room temperature. So these values comes from the literature. These are literature values, and these are measured at room conditions. So that's why this method is a little bit limited at room condition or ambient condition. So if you would like to determine the dispersive surface energy, you need to inject normal alkanes. If you inject the alkanes, you can get the alkane line, and from the slope of this line, the dispersive surface energy can be determined. If you inject the alkanes in a series, so at different concentrations, you can determine the surface energy at different averages. And this can be used to determine the surface energy distribution, the energy heterogeneity of the surface, uniformity, surface energetically. Once you have the alkane line, and if you inject the different polar probes. The specific Gibbs free energy of polar solvents can be determined, which is the vertical difference between the measured polar point and the projected data points on the reference line. For the specific surface energy calculation, we determine the acid and the base parameter. It's the extended Fogs theory, and then this acid and base parameter can be used to calculate the specific part of the surface energy. So we determine the specific Gibbs free energy of dichloromethyl and ethyl acetate, and then we can determine the specific surface energy. So 2 monopolar probes are needed to determine the specific surface energy with this method. Once we have all the different components of the surface energy, so the dispersive, acid, and the base, the work of cohesion and adhesion can be calculated. These 2 cohesive and adhesive energy are important in formulation design. So it's used to determine the blending performance, the uniformity of the blend. The surface energy can be measured with other techniques as well, like contact angle or atomic force microscope. In this table, you can see a short summary and comparison between these techniques. If you are interested in a more detailed comparison, you can visit our website. Just to highlight a few differences between these techniques. So with IGC, you can measure the surface heterogeneity. With contact angle, you actually measure just a single point of the surface where the drop is placed. Of course, if you perform that drop in the different part of the surface, you can get a bit bigger picture about the surface. In case of AFM, it's kind of 3-dimension measurement, and X, Y, and the Z is predicted. During AFM measurement, the humidity or the temperature is not that controllable. Like in case of IGC, you can change temperature or the relative humidity. Reproducibility is also much better in case of IGC than contact angle or AFM. And in case of IGC, you can perform the experiment on the same sample. While in case of contact angle, it's really hard to perform the measurements on the same surface where you already measured the surface, the contact angle. Especially if it's a powder or a sample which can absorb water. In case of powders, and you use contact angle, you have to create a flat surface. So you have to compress the surface. And then you put this drop on the surface, measure the angle. You see that over the time, this drop will penetrate into the part, will swell into the sample. So there can be dissolution, and these are the disadvantages of this technique. So it's not really applicable on powders or porous materials. There's also several publications which highlights that for heterogeneous high energy surfaces characterized by IGC at infinite dilution, solute will preferentially probe the high energy sites, and the technique will lead to surface energy value higher than those obtained by contact angle measurement. So which means that the surface energy measured by contact angle is lower than by IGC, because with IGC you can probe the high energy sites and you can measure the highest energy sites. It also means that contact angle measures the surface energy at a different coverage, and of course surface energy is changing with the coverage. So, for example, the dispersive surface energy value determined for conducting polymers by IGC were found to be always higher than those estimated by wettability. So there's a lot of publications which already highlight that it's not easy to compare the surface energy values measured with two different techniques straight away. And it can be also different, the surface energy measured with different techniques, because they measure in the surface energy in a different dilution, different coverage. There's other publications as well which discuss the differences between contact angle and IGC. And it was found that the IGC is more accurate on porous materials and powders than contact angle. During the surface energy measurements, it's really important that you have to be in an infinite dilution. So you inject the probes in infinite dilution, whereas only solute and solid material interaction occurs. Compared with the BET, where you have to really saturate the surface with the adsorptive, so you have to both a monolayer coverage, so the surface is really saturated with the probe, the solute molecules. In case of surface energy, you don't need to. You need to be in the infinite dilution. The theoretical infinite dilution surface energy, the gamma zero or the gamma infinite, is always an extrapolated value to zero concentration from the intercept on the plot of surface energy versus injected amount. And probing with the smallest concentration of solute and getting the most data points in this infinite dilution range, whereas only solute-solid interactions occur, yields a superior data fit and extrapolation to zero concentration when compared with other techniques where you can't really measure a series of concentrations. Also, real surfaces are often heterogeneous energetically, and the series of concentration in the very low solute concentration range, which reflect only the solute-solid interaction, will allow to determine the degree of heterogeneity of the surface energy distribution. Because real materials display surface structural and chemical heterogeneity, which in turn gives rise in their surface energetic heterogeneity. For example, structure heterogeneity can be crystal imperfections, some surface irregularities, or surface pores. Some chemical heterogeneities, like a surface contaminants, some chemical degradants on the surface, and so on. So real materials often has a energetically heterogeneous surface. So you can, with IGC technique, you can determine the surface energy heterogeneity if you probe a very, very small concentration in infinite dilution. So starting with the very, very small concentration, or you can go below 0.5% average. But if you inject series of concentration from all the solvents, from the different alkanes and the two monopolar probes, you can determine the surface energy heterogeneity. And during the analysis, what you have to always check is the regression coefficients of the alkane line. And also that the polar probes should be above 0. In this case, you can see dichloromethane is around 0. It's because the retention time of the dichloromethane is very, very small. But if all the coverages are good, in this case, because dichloromethane the 0 free energy, we used the chloroform to determine the surface energy distribution of this paper. And you can see the distribution graph, what you can get directly from our software. Just one more thing I would like to mention, that surface energy can also change with the relative humidity. So if there's a humid environment, surface energy can change, it can decrease, or sometimes also it will not change or it will increase. This example is on a cement paste. So the surface energy is significantly decreased if there's around 20% or 30% relative humidity. But after that, it didn't change much. So thank you for your attention, and I'm happy to answer your questions.
Thank you, Anett, for your presentation. So yeah, I would like to ask everybody if they have any questions. You can write them in the chat box or unmute your microphone. So I have one question. So what is the minimum limitation for IGC to determine BT surface area? And is it possible to determine some metal powders, which would be difficult to get some reproducible results with nitrogen adsorption method?
Certainly, yes. We did a few studies on metal powders, and we got a very nice results. So we can determine surface area as low as 0.05 meter square per gram. So we can go really down in the surface area range. Due to the pulse injection, our instrument has a higher limit in surface area, but in lower end, there's no limit. So far, we haven't experienced lower limit.
Okay, thank you, Anett. I have another question. So thank you for the case study for the humidity effect on surface area. And does the humidity have an impact on surface energy as well?
It does, yeah. As I showed on the last slide, surface energy can affect, humidity can affect the surface energy as well. So in case of this sample, cement-based, you can see a decreasing trend with the relative humidity, but sometimes there's another trend. Sometimes there's just a slight difference along the relative humidity. Here, so you can see the surface energy drop significantly at the very, very small relative humidity.
We've just got a comment just saying for BET, we must be very careful to choose the appropriate amount of injected octane. So I guess how would you choose the amount of injected octane for BET calculations?
I always just start with the highest achievable coverage. I usually use the coverage injection. In that case, of course, the achievable coverage range, it depends of the BT surface area what you entered into the sample ID. Once I entered the BT, initial BT, just estimation that where I expect BT. Based on that, the software will calculate the achievable range, and then I start with the highest and then go down to the lowest to get the whole adsorption isotherm. Sometimes, yeah, if you underestimate or overestimate the BT, just try to find it. Yeah. So as you see here, so I start with the highest achievable and then go down to make sure that we'll have enough data points in the BT range. And of course, you have small relative pressure points, but then you just have to adjust the settings, the method settings, and then rerun it. That if you start with the highest available concentration after the first injection, you can modify your method. You can stop or edit the method based on that first injection. That's why I just start with the highest, so I can modify after the first injection. Yeah, sorry.
Okay, thank you. We have one more question. So thank you for the very informative session. And for polymeric fibers which absorb alkanes, what is the best way to measure the dispersive part of surface energy?
In case of our instrument, we designed the injection that we have a target concentration what we inject, and at the end of the experiment there's an actual coverage, so we can see that is the sample really absorbed the injected probe molecules, is there chemisorption happened. So that's why we have this target and this actual coverage, just to double check that is there any chemisorption or absorption of the probes into the sample. And of course, if you see a significant difference between target and the actual, that can mean that maybe there's chemisorption or absorption. But you can try to increase the temperature, maybe because just temperature is not enough high, or you have to put more energy into the system to desorb the probes. So you can try first to apply higher temperature, maybe because just the desorption is much slower, so it requires more energy. So higher temperature can help, but if higher temperature will not help, then probably it's really chemical chemisorption. So you have to choose another probe for the analysis. Maybe to measure dispersive surface energy. There's some not very well established, but some new methods which are based on aromatic hydrocarbons instead of normal alkanes. So I recommend to have a look at the literature, but also I can help to find some solution for that, to measure dispersive surface energy of this kind of samples.
So just to follow on from the question, will humidity help?
I don't think so. Yeah, because with humidity you measure another effect. So I wouldn't use humidity at the beginning. And just first, I would try to find the best parameters to absorb and dissolve the probes, and then move on to humidity.
Okay, thanks, Anett. There's another question. So if I get very bad noisy peaks for ethyl acetate, can I use chloroform to determine the surface energies? And what are the alternative monofunctional solvents that I can use?
I mean, if the ethyl acetate is very noisy, I recommend to use toluene. That might help. And yeah, you can use chloroform. That's for the other part. That's for the base part of the specific surface energy. And also dichloromethane is an alternative. In case of our software, you also have opportunity to change this. So for example, if you measure the acetone surface tension parameters, the acid and the base, and you wish to use acetone, in the analysis software, you can change the acetone or ethanol or any other polar probes surface tension values on screen, and then you can select those probes for the surface energy calculation. So it's not limited for our recommendation. These are just the probes what we use, and it's based on the literature. But of course now science improved, and there's other ways to measure surface tension parameters of liquids. So if you have new values for other polar solvents, you can use them. You can enter into the analysis software. If you wish, I can contact directly with me. I can show you how you can do that and how you can use any other polar or specific surface energy.
Okay, in that case, I would just like to thank everybody for joining. And if you wish to know more about the DBS or iGC-SEA systems or its applications, please do visit our website, or alternatively, you can email us at science@surfacemeasurementsystems.com. Thank you.